All right. Today's going to be a little bit more towards lecture style than I prefer because I'm kind of fragmenting this topic into pieces, and most of what I would do to talk about mass that actually has a demonstration component to it fits a lot better when we do gravity, which I'm doing separate, just so that I can fit a couple of questions into this first exam that are more fitting for how short of a time scale I'm throwing this first exam at us. So along with doing what we're doing today, I'm going to do a little bit of going back and doing management of class type of things now that you've had some time in the class and I've seen how it's running with actually doing demos. Hopefully this is the last time that I sit around chatting about how the class is until midterm-ish, when I come back to check how are things going, what do you feel about everything. 1 minute papers isn't something that I had pictured doing during the whole 1 week I got to prepare for you guys. And then at a conference, I saw people talking about how good they are for getting students engaged. So I just wanted to check with you guys, since it looks like I'm doing one every single day now. I don't have the time to give you all feedback and get them all back to you. There are misconceptions in there. It's not at the point of, oh my God, the majority of the class isn't getting this, but it is at the point of, oh, I really wish I could talk to them about these specific problems. So I just wanted to feel out with you guys, is 1 minute way too short? You'd like to have more time to think. Would you like to chat with each other, check if the guy next to you can find flaws in your argument? Would you like me presenting to you? So if you haven't had a chance to answer, hopefully you did during this ramble. And taking a quick look, by the way, there's no actual need to respond to this one. It's not graded one way or the other. And I think I have to scroll, don't I? A little bit. Okay, so yeah, you guys would like feedback from me, and there's a fair number who don't really like it. Possibly some of those are, they also were saying there's ways to improve it. If you were, can you go back and take off the not useful? I want the not usefuls to just be the people who flat out are saying, stop making us right. And it looks like nobody really feels that way. So I do have another 1 minute paper. Those of you who are now more so deciding you don't like it, I will reflect on that and try to cut back on how much I'm doing, and I will try to come in and say what the right answer is. This is also the last day of content which will be on the first exam, which is the second half of class this Friday. It is a small, tiny little exam, so those of you with test anxiety, don't. Not that that helps. There's one option to do an essay type of response, where you need to keep in mind what the big topics are, and that you're looking to get 10 points. So there should be at least 10 times that you refer to those major topics. The other option is to do multiple choice questions, 9 of which are in the homework. And you'll be seeing, again, not necessarily with the exact same wrong answers, and I might change the flavor of the problem so you can't just rote memorize. So they will be carbon copies of what those were. But you can't just memorize, okay, this is what the thing said was the right answer, I'm going with this. But if you understand the homework, you should get a 90% on the exam at the least. With homework, if you have questions, ask them. In class, when I say, do you have questions, I really and truly mean it. We're not on this time crunch where I've got a certain number of slides I must get through. This format is supposed to make it more engaging, more capable for you guys to ask for help. That's the whole reason I'm here, is to help you. So if you have a question about something, ask it. When we get done with the 1 minute paper, if you say, wait a minute, don't move on, what was the answer? That reminds me to say what the answer is. The 1 minute paper we did yesterday, today I actually wanted to talk about what specifically the answer is, and that was that I asked you, what does it mean when I say that friction flies in the face of Newton's first law? Let me close this down real fast. All right, not useful is outweighing. So, the people have spoken. You guys don't really care for 1 minute papers. but I'm still going to make you do one because it's on my plans for today. And I told you in your pre-class assignment that we are going to do one. So here's the scenario. I don't anticipate any of you guys getting this right, and we are going to talk with neighbors afterwards. So you guys get 1 minute to figure out what your approach is going to be. Here's the scenario. You are on the International Space Station. The science demo that you've been asked to do by a class is that they've sent up 2 wooden boxes, completely sealed. You can't open them. One of them is empty. The other one is full of water. Now, you're on the space station. This is weightless territory. How can you, using the concept of inertia, tell which box is full of water?
How full of water is the one box? Just a little bit of water? Is it
all the way full? So there's a giant hollow cavity. They're both made of the same wood shell. One very empty, the other very full of water. What do you do using the concept of inertia to figure out which one's full of water? So inertia, the property of matter, from right, I-N-E-R-T-I-A. So that was in your pre-class assignment. Okay, time's up. Grab a neighbor, show them what your idea was, look at their idea. Hopefully you weren't both, I have no clue. If you have no idea, then just talk about what is this inertia thing. Maybe you guys didn't do the pre-class assignment. Okay, who wants to volunteer an answer?
I just say that you would use or apply Newton's second law because mass isn't dependent on gravity. Even though it's weightless, the mass is still there.
Okay, how would you apply Newton's second law?
Either by applying, testing the acceleration of both, or even pushing them both up and seeing which ones, or stopping both of them, and the one with the water should be harder to stop.
Okay, so that's more so Newton's first law. But to a degree, the second law comes in because it's the one with the equation. But it's that resistance to a change in velocity. That's what Newton's first law is all about. More mass, more resistance to a change. So how many had something along the same lines? Did anybody have something else that they think would work and they want to just try out? Okay, so his idea proposed was you hurl them both up into the air, and then you try to stop them. The one that doesn't have water is going to stop really easily. The one that does is going to take some more effort to stop. You can also just shake it back and forth. This is just like the video with Derek Mueller from Veritasium having people push his car. The mass is that resistance to the change in velocity, that resistance to acceleration. So when you're shaking something back and forth, you're accelerating it a lot. You're changing its direction of motion. And you're going to need a lot more force to do that. So anything you do that's going to make those move, you're going to notice. So yes, if you're out in space, you can hold up the space station because it's weightless, but you sure aren't going to push it into a completely different orbit, because that's you trying to change something about it. And that's where that fundamental concept of mass and weight are different. Weight is you fighting against gravity. It's you becoming that counterbalancing force to hold the thing up from being squished into the center of the Earth. Mass is inertia. It's the resistance to a change in velocity. So back to the 1-minute paper from Friday. Why does friction fly in the face of Newton's laws? Because we don't think of friction as being a thing. This actually goes back even further than Newton. Galileo was the first person to say, well, maybe Aristotle's wrong. Aristotle said the natural state of everything in the universe is to be stationary. Everything wants to stay still. So if you roll a rock, it will stop because it wants to stop. That's its natural state. Something has to keep pushing it the whole time that it is moving. And so there's this strange force after you've let go of it with your hand that's continuing to push it. Otherwise, it would just stop. And a lot of people in their head, they still think if something's moving, there is a force on it right now. And that's not true. There was a force on it once upon a time that gave it that motion. But if nothing's touching it, there's not necessarily a force on it now. This being said, assuming you're ignoring air resistance, friction, which is the force that's going to be slowing it down to eventually stop. So because of friction, it's hard for us to see the truth of Newton's law, because in our experience, nothing just keeps moving forever until stopped, because we are trained to ignore the thing that is stopping it. We don't think of friction as an outside force. And that needs to change when you start thinking in terms of physics. That's one of those, we ignore the way the real world works so we can better understand how the world does work the way that it does. We have to ignore friction in order to get the nice, simple, elegant formulas that work out remarkably well, as long as someone's life doesn't depend on it and you need to really and truly count for friction. When we're talking general sense, ignoring some things is great. So friction makes it harder to accept Newton's laws. And Newton's laws are built back onto way back in Galileo's time. Now Galileo did something else that plays in with this whole concept of inertia that we're going to revisit more when we get to gravity. But you guys have probably all heard about the whole heavy object, light object, which one's going to hit the ground first? How many of you say this one? Okay, good. Then there's absolutely no point in us doing this because you all understand. This is one where, going back to the one equation that we are using so far, comes in handy. So, F equals ma. That is what plays in with this. Now, when these things are falling, what force is pulling them down? Gravity, which we can see as just a special acceleration. So F equals mg is pulling them down. Now the reason they both fall at the same speed is because the acceleration that they are feeling, the acceleration on each of the balls is the force divided by their mass. So this is the acceleration felt by the ball. This is the force exerted by gravity. So if we replace this force then you guys should all be familiar enough with algebra to realize this is why mass doesn't matter. Their masses cancel out because it's the same principle. It's that Newton's second law that is the reason why it's moving and the reason why it's resisting the motion. So that bigger object, that more massive thing, does feel a larger force from the pull of gravity pulling it towards the Earth. It has a larger mass here. But at the same time as it gets that larger force, it also resists the change in motion more. So we'll come back to all of this when we talk about gravity. I believe next week, probably about Wednesday, is when I've got that one slotted. Now, along with this idea of things falling and moving and traveling all around, there's two key terms that will be used in problems I give you guys that I don't know if the colloquial terminology matches up. The first one is free fall. And I don't have any fancy questions or slides or anything to go with that because I can't think of any other way to possibly consider it. It's just one of those things you're going to need to keep straight in your head if it's not already that way. Free fall means something is not attached to anything else at all. It is falling freely. We will almost always be in Earth when we're talking about something in free fall, which means there is a force acting on it, and it's just this one. So something in free fall has this force and nothing else acting on it. The other one is terminal velocity. And on that one, I can think of some possibilities. But I'm hoping most of you already understand what terminal velocity is. And so that's why I'm throwing this up here, so I know how much time I really need to spend on the idea. Oops, wanted to see the reports. Okay, so we really don't need to spend time on it. Terminal velocity is the fastest speed that something reaches. Now it can be different in different cases. In almost every case, when we talk terminal velocity, and by the way, it's not Van Damme, it was actually Charlie Sheen, and it was a terrible movie anyways. When we talk about terminal velocity, most of the time we mean air resistance. Now, what is the air resistance on something which is falling at terminal velocity? Can you say exactly how much air resistance it has then? Zero air resistance? Say that last part again, the air resistance. Yes, which means the air resistance is not zero. So look closely at what you said. The air resistance balances with, not the rate, the weight at which you're falling, but the, so what would the air resistance be? Which is? There you go. So you had the exact right key in there. And this is something I want to point out for the exam that's coming up. If you're not sure about your answer, or if you want to say an answer that's not in there on the multiple choices, be willing to explain it. Because right there, you would have gotten that wrong on the exam. You would have circled the wrong one. You would have said air resistance is 0. But if you explained it exactly the way you just did, I would have seen you do understand it. You just don't have the terminology. And I would have given you all the points. Because the net force is the thing that is 0. Because the air resistance is canceling this force. So you're getting pushed up exactly as much as you're getting pushed down, which means your net force is 0, so your acceleration is 0, which is why your velocity is not changing. It is the highest speed that you will travel at. So if you're spinning something around, its velocity is not constant because it keeps on changing directions, but you could refer to that as having a terminal speed if there's a single controlling force that's making it spin. But at this point I'm confusing you guys, so I'm going to step off that. Okay, back up. Terminal velocity, most all cases. Air resistance is pushing up exactly as much as gravity is pulling down. It can also apply to traveling horizontally. Forgive me if you actually understand how drag speed racing works. I'm going to assume drag speed racers, giant cars with essentially jet engines strapped on the back of them, trying to get to the end of the track as fast as they can. My assumption is they're not actually accelerating the entire time. Yes, they're burning the engine the entire time, but at some point the friction on the road is going to be pushing, and the air resistance is going to be pushing back on them enough to cancel that out. Now, drag speed races are really short, so I'm probably wrong. But if we go for a land speed record instead, same basic concept but in a giant desert. You push as hard as you can with as much force as you can, but you still have drag, you still have rolling friction. Things can work against you. So even then, you can hit a terminal velocity. The term just means the highest velocity that you reach. And that's because the forces cancel out. Which gets us into the next lovely tool, which, in order for us to avoid a lot of the math, we are probably going to hinge on a lot. And that is force diagrams. So if you guys are all really comfortable with vectors in general, then basically we're done today. There's nothing else we need to do. The difference between mass and weight, and then being comfortable drawing out all of the forces that are on something so that you can consider them against one another. So if we have an object, unless I specifically say lots of complicated stuff to get us away from gravity, you always get to throw on the force due to gravity. And I really should be writing this down by the arrow so it stays away from everything else. Now I think at some point in the videos I had you guys watch, it mentioned why we put everything in the center of mass, just so we can centrally locate it. And that much later we'll start talking about torque, which is where it finally matters where the forces apply. We're sticking to the put it all in the middle. Except when we go in to do vector addition. Now when you're drawing these, I'm not going to be getting out a ruler and trying to really carefully nitpick you. As long as eyeballing it seems like things work out, we're good. Especially if I see on the side that you tried to figure things out. So if this is sitting on a table, like that ball is right now, if we're doing the force diagram of that ball, am I done? Why not? What tells you for sure that I'm not done? Because we have a net arrow, and that's not moving. If we have a net arrow, that has to be sitting still. So yes, something has to match it out. And for that ball, lovely, I grabbed a dead pin from the brand new pile of pins. Nope, they just all look really dim. Okay, so this arrow, in order for all of this to be sitting still, should be about the same length as this arrow. And that is the normal force, which means it's the force of something pushing against it. And things push perpendicular to their surfaces. So if I incline the table, what should happen? Well, however much I tip the table by, that's going to shift this normal force, which is going to result in an imbalance. Now, will the ball jump off the table? Will it levitate? Which means that this height should still be matched to that height that the force of gravity was. Because in that direction, in the direction of gravity, it's not getting to go up. But what did I just forget? What does happen to it in the direction of gravity? It going down a little bit. So minus a little bit. So it can still go down. Now this is where the vector addition stuff comes in. Vector addition, you draw them tip to tail. I'm going to assume you guys are comfortable with this. If you're not, catch me during office hours, email me to set some time up. We can talk about how to do vector addition. But you take this same thing and you draw it tip to tail. So these two should be parallel to each other. This should start where the other one ends. And your net force is this, which would be, ideally, parallel to this. So I really wanted it to have come out right about there for where I end. And throwing on these extra little sketches to get your arrows just right is helpful and gets you the nitty-gritty extras. But you don't have to spend all of that time when we do a force diagram, because I'm not expecting you guys to be artists. You don't have protractors and compasses to do everything flawless, perfect. I'm not requiring you to be on graph paper. As long as you have each of the relevant forces pretty close to what it should be, especially if you write in extra notes saying this one should be roughly this, or the net arrow should be something parallel to the surface of the table because it's traveling along the surface of the table, then all of that helps. So don't worry about your artistry is going to cost you points. If you want to explain instead of write, that's okay. This is supposed to be a tool that helps you to make sure that you remember all of the forces. And if we start getting into more complicated things like how does an airplane fly, it becomes a whole lot more useful. And I am hoping that at some point we'll have enough time in class that we can go over a full description of exactly how airplanes fly, because that's a lovely allegory for why it's so hard to teach physics. There's a lot that goes into it. Professional airplane designers and pilots will argue with one another because they're in two different camps about how you should properly explain it. But instead of realizing it's just they're talking about how to explain it, they argue that that's the way it actually works. And the truth is, it's really dang complicated, and we try to make it simpler, but any way of making something simpler means making it wrong. And so most of what I'm teaching you guys is wrong in the technical, full, you understand everything sense. But all of this stuff is true to an approximation or given certain foundational steps. If I wanted to be teaching you Newton's laws completely and totally correct, we know Newton's laws are wrong. Flat out, complete and utter useless. If you're moving anywhere close to the speed of light. Since in our day-to-day life we aren't, these are a fantastic approximation. They come out really well. But you have to throw in relativity for them to be correct. And even then, that's where you get into how science in general works. Nobody says this is the way the universe is, even with all the relativity and everything thrown in. Science is always open to, oops, we forgot something, let's throw that in there. That's why we make sure to state our assumptions. And if you do that on your exam, if you say, this is my assumption, and with your assumptions, it's correct, then okay, I worded the problem poorly, you win. As long as your assumption isn't assuming the answer is A, the answer is A. You can't get away with that. Okay, so one more to see if you guys are good on the idea of free fall. And I forgot to delete a blank question mark. I'll give you guys a hint, it's not D. So you're flying in a plane, the engines just completely stop working, plane drops. What do you experience as passengers? Now you guys have all driven in cars at the very least. You know when a car turns a corner, you're driven over to the side. Is that the same thing that's happening with the plane that drops?